All right, today we're going to be talking about different types of interest, like simple and compound interest. We'll also be talking about exponential growth and decay. Okay, so what is exponential growth? Okay, exponential growth is something that is growing exponentially or getting larger as we go to the right on our graph. As our values of x increase, my values of y are increasing exponentially. So here is usually what we use as a parent function here, 2 to the x. Okay, so as we define what would represent growth and decay, we need to have positive values for a and b in this formula. So this multiplier in front has to be positive, or most like our negative a values would be getting a reflection of a growth graph, which does not model growth or decay. B, our base, also needs to be a positive value here, so we don't get what looks like kind of like an oscillating series. And it cannot equal 1. The base cannot be 1, because 1 to any power is just 1, and it would not be growing. Okay, so for positive values of a and b, and our base not equal to 1, we will have exponential growth if our base is greater than 1. So anytime we are larger than 100% or greater than, let's just say more than. When we are more than 100%, and you can think of 1 like its decimal version representing 100%. If we're above that, we're growing. If we're between 0 and 1, remember b can't be negative, but if we have a fraction that's between 0 and 1, like 1/2, we get a graph that looks like this. We are cutting our value in half every time we go to the right, and my values get smaller and smaller and smaller, and in fact get infinitely close to 0, but never technically gets there until you hit infinity. So when we are less than 100%, that's called exponential decay. So between 0 and 1, so a half, right, would be like 0.5 between 0 and 1. That is exponential decay there for our base. Okay, the growth or decay rate is the percent above or below 100%. It's what we refer to as the decay rate, growth or decay rate. So let's do some examples. Identify each as the exponential growth, decay, or neither. Okay, identify each as exponential growth, decay, or neither. Identify the growth or decay rate for any growth or decay. So find the actual rate. So first thing we need to check, remember that a and b need to be positive, and our base cannot equal 1. So let's first check. This would represent a, it's positive. B is also positive, and b is also not 1. So it passes all of our check. That means we definitely have either growth or decay here. And to figure out, we need to look at the base. Is that greater than 1 or less than 1? Well, we can do the division. 3/2 is the same as 1.5. So that is greater than 1, which means we have exponential growth. So this is an exponential growth problem. And now we can look at it. Now I know I'm growing. We're above 100%, right? We're above 1. Well, how far above 1 are we? We are 0.5 above 1. Which means, and remember this really represents 50%. So this is a 50% growth rate. So 50% growth. Okay, let's try number 2 here. First, let's check that a and b are both positive values, and they are, and that my base is not 1. Okay, good. So now we know it does represent either growth or decay. And obviously looking at my number, we're above 1, right? So I can tell right away this is definitely growth. And then how far is my base above 1? Well, if you subtract 1, we are 1.25 above 1. Which means we actually have a 125% growth rate. This is growing very, very quickly. Okay, number 3. check my A and B values, make sure they're both positive. Uh-oh. Now, because A is negative, this is not modeling growth or decay. In fact, it's actually the one that would look like, this graph, but a reflection of this graph because A is negative. So it's a reflection of growth, but it is not technically modeling growth. So this is neither. And if it's neither, then we don't need to identify the growth rate. This is just a reflection of an exponential growth graph. I hope you guys enjoyed that sneeze in the background. All right, our next one, 500 times 0.84. So let's check. They are both positive, and my base is not 1. So good to go. It's definitely growth or decay. Ooh, this time my base is less than 1. So this is a decay. This is exponential decay, which again would look something like this, depending on our decay rate. So how far below 1 are we? Well, let's take 1 and subtract 0.84. And if you do your bunch of borrowing here, we get 0.16. We are 0.16 below 1. So we'd say this is a 16% decay rate. It's decaying at a rate of 16%. That means we are losing 16% of our value every time x increases by 1 full unit. So if you start with, say, this would be like starting with maybe $500. Every time a unit of x increases, I lose 16% of my remaining value. Okay, so here are a bunch of formulas that we're going to use today. These are the different types of interest. So we have one called simple interest. This isn't used too much anymore, but sometimes it is. Compound interest. This is most commonly used. And usually if they don't specify the type of interest, it's usually compound. And then there's also another one that's not used very often, but it is called continuously compounded interest. Okay, so what do all these letters mean? And they're very similar through all of these formulas. A is the amount we would have after t years. So t is our time in years. P is something called the principal, and this is spelled P-L-E, not P-A-L. Right? You're supposed to tell the difference. The P-A-L, the principal, is like your friend, like Miss Ditto. But principal, P-L-E, is what we're talking about here. This is actually like your starting amount. Okay, it's called the principal. So how much money you put in when you're investing, etc. R is your interest rate. This has to be in decimal form. So if it is a 5% interest rate, that is 0.05. Not 0.5. That would be 50%. That would be nice if I got that interest rate, but that's not probable. Okay, T, as we discussed, is time in years, and N, which only occurs in this formula here, is the number of times compounded per year. So sometimes they compound your interest more than once a year, like monthly or weekly. So if it's monthly, we'd plug in 12 for N, etc. Okay, so let's check out some problems with these. So we're going to use this for all these different types and look at the amounts we would get. So given a $5,000 initial investment, okay, so we actually know that P here is 5,000. That's our principal initial investment. And yearly interest rate of 4.5%. So again, now I know there's a decimal in this, but it is not in decimal form. Move your decimal over twice, and that's actually 0.045. So again, to convert from a percent to a decimal, move your decimal left twice. There is our interest rate in decimal form. Find the amount, so find A, for each type after 10 years. So T, our time, will be 10 for 10 years. So it wants us to start with the simple interest formula. That's this one. So let's go ahead and write the formula. A equals P, our principal, plus our principal times our rate times time. Okay, so let's go ahead and plug in. My principal is 5,000 plus 5,000 times our interest rate, 0.045, times our time in years, which is 10. So now we just need to go to a calculator to find this value. Okay, so here we are. You're using Desmos to find our value. we get 5,000 plus 5,000 times our 4.5% times 10 years. Tells me in my account, we will have $7,250. $7,250. We'll go ahead and put some change at the end because we're talking about money. Okay, so that's how much money I would have if I got a simple interest rate of 4.5% and left it in there for 10 years. Let's see how that compares with some of our other rates or other types of interest. Okay, so now we're going to talk about compound. So if something is compounded once yearly, the number of times compounded per year becomes 1. If you actually plug a 1 in those two places for n, your formula simplifies to this. This is the nicer, kind of simpler one when it's compounded once per year. So they are the same formula essentially. This is just when n is 1, or it's compounded once yearly. So we're going to go ahead and use this nice, simpler looking version. So our principal times 1. Now it says plus or minus r. That depends if we are gaining or losing this percentage, right? Whether it's growth or decay. Now we're assuming we're investing, and we're talking about gaining 4.5%. So we're going to put plus, because our value is going up, 0.045 to the t power. Oops, sorry, that was just supposed to be r. I was just writing the formula. To the t power. Okay, so it is plus this time because we're going up. And let's go ahead and fill in our values. The principal they told us was 5,000. We're still using the same problem from above, just a different formula. Times 1 plus our interest rate, 0.045, to the t power, or 10th power. Okay, and yes, you can add these together and you can make that 1.045 to the 10th if you'd like. And that does show you, by the way, that we're above 100%, right? As we talked about earlier, we are 4.5% above 100, so it's a 4.5% interest rate. So let's go ahead and go to our calculator and see what it gives us. All right, I went ahead and used the one where I added 1 and 0.45 together. It doesn't matter, you can use either form there. But our answers, this time we will have $7,764 and about 84 cents. Now, I know we really would like to round that up, but imagine you're a bank paying out your customers. Are you going to give them that fraction of a cent? Or are you going to round it off and keep that fraction of a cent? So logically here, the banks are in the business of making money. They do not round up for their customers. So what you would be expecting back is that they round off. They don't help you out, sorry. So $7,764.84. Okay, so actually quite a bit more, right? We're talking about already like 510-ish, $514.84 more. So that's good. I'd definitely rather have compound interest than simple interest. But what about if it is compounded monthly? Ooh, that is 12 times per year. So that's 12 times per year, which tells us actually n. That n value we are going to need to use is 12, right? N is the number of times compounded per year. Okay, and this time, because it is being compounded more than once per year, we do need to use this slightly more complicated formula. So I'll go ahead and write that down. A equals P times 1, again, because we're going up in interest, plus R over N to the N times T power. Okay, so let's go ahead and plug in. My principal, our starting amount, is 5,000. 1 plus, now my interest rate is 0.045 over N. And because it's compounded monthly, N is 12. And then up here in my exponent, we're going to have N times T. So 12 times T, which was 10 years. So our exponent ends up being 120 there. So yes, you could calculate this decimal here and add 1 to it. I'm just going to go ahead and plug it in like this. Okay, here we are plugged in. Now, Desmos is a little finicky about keeping you in the exponent here. So I just went ahead and you can either put parentheses and write 12 times 10, or you can just raise it to the 120th power without parentheses. But make sure your exponent does end up being equal to 120. So here's our value. We're a little bit more. If you notice, $7,834, and again, 96 cents. They are not rounding up for you. Not that we would round up here either way, but just be careful with that. Okay, so as you notice, again, we've gone up in value. But what about if we compounded instead of 12 times per year? In fact, let's go ahead and make this 12 times 10 up here, just so we can manipulate these values. So there's an excessive number of parentheses up here in our exponent, but there we go. What if we change some of these values around? What if instead of 12 times a year, monthly, what if it was done weekly? Well, that would be roughly 52 times a year. So what if I change that exponent to 52? And it looks like it's going to be a lot more money, but don't forget we end up dividing our interest rate also by 52. So let's see, did it go up if we compare? We did, but we're talking about under $6. But it did go up. What about if we compounded daily 365 times? But don't forget we end up cutting our interest rate into 365 parts. Well, we went up about $1. What about if we did it hourly, or every minute, or every second, or every instant? Would we get more money? And as we can tell from our trend, the answer is yes. And that leads us to our last one here. Something called, I need to move that down, called continuously compounded interest. This is interest that is compounded like every fraction of a second, like continually, the most number of times you can compound possible. And guess what ends up being in here? That is our natural number E. That is not a variable. That is Euler's number, aka the natural number. So that's pretty cool. So our formula looks like PERT, P times E to the RT power for continuously compounded interest. Well, let's plug in our numbers. That's 5,000 times E to our interest rate, 0.045, times T, which is 10. Well, let's check out our calculator. This would be the maximum amount I could get from compound interest. And there we go. Not much more than when we talked about daily. Maybe a few pennies more. But this is the maximum, $7,841.56. All right, what about if compounded once yearly, how long in years would it take to reach $20,000? Okay, so I guess we're starting with the same amount here, and it's compounded once yearly. That's this formula. Remember where n is 1. It's our nice simplified formula. So it is compounded, compound interest, and once per year is the nice simple looking formula. So if we use this, let's go ahead and plug straight in. Now the amount A that I want to have is the 20,000. That's what I want it to equal. We do know our starting amount, the principal, is 5,000 times 1, and again our interest is going up, so plus 0.045, the decimal version of our interest rate, to the T power. And that's what we're trying to figure out. How long, I don't know why there's a period there, in years, which would be T, would it take? So our unknown here is T. Well, in this case, we are going to go ahead and add the 1 and the 0.45. And you might note that because my unknown here is an exponent, what do we use to solve for unknown exponents? Logarithms. We use logarithms. And what we're going to do, just like when we were solving these in the previous lesson, we need to get that base of our unknown exponent by itself. And that 5,000 is held to with multiplication. So we're going to divide. Divide both sides by 5,000. Okay, so we divide our 5,000 away. Over here, 20,000 divided by 5,000 ends up being 4. And we probably don't even need the parentheses over here anymore. But note, now we have our base by itself. We can go from an exponential form to log form. Or we can use log base 1.045 on both sides. Okay, but if we're just changing this from exponential to log form, which is one way of manipulating this, that would be a log with base 1.045 of 4 equals t. Now again, you could think of this as doing log base 1.045 of both sides. Then you'd have to do the same over here, log base, 1.045. And then these cancel, and we get the same expression, right? So either approach is fine, but we should end up here. And now we got to go to our calculator. But my calculator doesn't do this base, so we need to use change of base formula. Now you can use any base you want, log or natural log here. It doesn't matter, they will give you the same ratio. But remember to drop the base, put the base in the bottom here. So this is going to be equal to t. Let's go to the calculator. All right, here we go. Log of 4 over log of 1.045 is about 31, and let's go ahead and say about a half. How long in years is it going to take? About 31 and a half years. Now just to remember that you can do log, you can do natural log. Those are, most calculators will do those. You can see it still gives you the same ratio. So you can choose which one to use there. When you use change of base formula, log and natural log are in all calculators. But there's our answer. It's about 31 and a half years. All right, we will definitely do a bunch more interests like this, some more we're solving in class. We'll also talk about the importance of investing early and why that's more important than how much money you throw in there. So make sure you're at class. Pretty good lesson. See you later.